You're here because you want to master relative atomic mass and relative molecular mass with a University of Cambridge graduate. This is actually part 1 of our mole concept lecture series. So if you want to check out the rest of the mole concept lectures after you're done with this one, please be sure to check out the playlist or the link in the description below. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Before we begin, be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. Mole concept is a very important chapter, especially in the whole of chemistry, because it is the first time that you'll be learning how to do your calculations in the world of chemistry, right? And you realize that everything in chemistry revolves around this mole concept. Okay, so to kick things off, right, we'll start with defining what is the relative atomic mass. Relative atomic mass is the ratio of the weighted average mass of an atom of an element to 1/12 of the mass of the 12 carbon atom. So why do we compare to 1/12 of the mass of a 12 carbon atom? It's because back in the day, they realized that carbon is one of the most accurate in terms of like mass relative to grams. So 1 mole of a 12 carbon atom was found to have like 12.00000 and then something, a few decimal places, but it's very close to 12 grams itself, right? So everything was weighed relative to this 12 carbon atom. You can think of it that way. And why do we say it is the ratio of the weighted average mass of an atom? It's because, right, an atom can exist as different isotopes. Okay, and because of this, we know that with all the different isotopes, right, they're going to have different masses. Remember, because isotopes have different number of neutrons but same number of protons, right? So they have different masses and they're going to exist as different relative abundances. So their natural relative abundances multiplied by their isotopic mass, and when you add it all up together, you get the relative atomic mass, which is like the what we call like the weighted average, right? So for relative abundance questions, it's very important to know, right, the relative abundance of each isotope, right, multiplied by the mass of each isotope, and you add it all up together, you get the relative atomic mass. So you must know this formula very well. Okay, so let's take a look at some examples of how we can apply this formula. So for carbon, right, there usually is carbon 12 isotopes and carbon 13 isotopes, and carbon 12 isotopes exist at a relative abundance of 98.89%. That means 98.89% of all carbons in the world, right, will be a mass of like 12, right? But 1.11% of these carbon isotopes will have 13 carbon itself, right? So to calculate the relative atomic mass of carbon, right, we will take 98.89, right, divided by 100 times the mass, which is 12, right, plus 1.11 divided by 100, which is the abundance again, times the mass, which is 13. So if you add this all up together, okay, you get a value of 12.011, right? Intermediate working, we usually leave it up to like 4SF or 5SF, right? And then we will convert it as a final answer to 3SF. Right, so the relative atomic mass is about 12.0, which is quite expected, right? We know that the relative atomic mass is around 12, right, based on the periodic table itself. Now for neon, right, neon, there's 3 isotopes with these relative abundances. So what you're going to do is you're going to do the same thing. You're going to take the abundance, right, times the mass. We just add it all up together, right? Abundance times the mass, the abundance times the mass, right? And once we do that, right, we add it all up together, you get a value. You press in your calculator, you get a value of about 20.187, which you convert to about 20.2 3SF right here, right? So this is how we calculate the relative atomic mass. One more example. So for potassium, again, same thing. There's 3 isotopes. They give you the abundances, so you have to go and take the abundance, right, and then you times all the masses. Okay, and then when we add it all up together, okay, you get a value of about 39.132. Okay, and if you round it, it's about 39.1. Okay, so it's no surprise over there. So you realize some of your relative atomic masses have a decimal place of like point something, right? Like a 0.1 or 0.2, right? And you're like, oh, but this is very different from the periodic table. Yeah, because the periodic table usually given in secondary school, right, usually is rounded to a whole number, right? But actually the more advanced periodic tables will have many decimal places in its nucleon number, right, in the periodic table. So from the periodic table, right, what can we tell is the relative atomic mass of a particular element, right? Usually the top number is the atomic number, right? And we call this the relative atomic mass. So carbon is 12, no surprise, the bigger number. And the below number, as we've learned before, is the proton number, right? So when we want to write down the relative atomic mass for these following elements, you just have to look at the periodic table and you can fill this up. So you'll see that for sodium, right, it'll be like 23, calcium will be 40, okay, oxygen will be 16, and then copper will be like 64. Okay, so these are the how you find the relative atomic mass from the periodic table. Now with our newfound knowledge, we can actually find the relative molecular mass now, which is the mass for a molecule, right? So the example over here of how we're going to do this is we're basically just going to tally up all the numbers of each atom, and afterwards we're going to multiply it by their relative atomic masses, and we add it all up together to get the relative molecular mass. So for example, for ammonium carbonate over here, right, you got to find all the different elements inside first, right? So you realize that nitrogen, right, and then you go and count, right? So nitrogen here has 2 of it because the NH4 plus ion has 2 of it, right? So there's actually 2 nitrogen atoms. And then for hydrogen, you have 4 times 2, which is 8. And then for carbon, there's only 1. And oxygen, there's only 3. Right? So when we find all of these out, we can actually tally all of it up together. So the MR of this compound over here, right, if we multiply all the elements' atomic masses, alright, by the number of each atom, you will get 2 times 14, okay, because it's the relative atomic mass of nitrogen, plus, then we move on to hydrogen, so it's 8 times 1, and then for carbon is 1 times 12, and then for oxygen is just 3 times 16, right? And you get a relative molecular mass of about 96.0 with 3SF, right? So this is how you calculate our relative molecular mass. Okay, so let's do some practice over here and try to find the relative molecular mass of each of these compounds. So for CO2, right, we can actually find the MR of CO2. Take note of my notation over here. It's actually important that all your calculations have some level of labeling, right? So I put MR of CO2 over here, which equals to, so there's only 1 carbon, so it's 1 times 12, okay, plus 2 oxygens, so it's 2 times 16, and you get a relative molecular mass of 44.0, again leaving it to 3SF. Okay, next is ammonium chloride. So if you're ever unsure about the molecular formula, just write it out, right? Ammonium is a NH4 plus ion, okay, with a Cl minus ion, so it's just NH4Cl. So once we know the formula, we can find the molecular mass, right? So this is just, there's only 1 nitrogen, so it's just 14 plus 4 hydrogens, 4 times 1, plus chlorine, which is a 35.5 over here. And this will equal to 53.5 overall. Next, for ammonium phosphate. Okay, so ammonium phosphate is a NH4 plus ion and a PO4 3 minus ion. So the overall formula is just NH4 3 PO4. Okay, and this will give you molecular formula of NH4 3 PO4, and you can then find the molecular formula. So this, the molecular mass is just 14 times 3 because it's 3 nitrogens, because it's 3 ammonium ions. Then there's 12 hydrogens. And then there is a phosphorus, right, which is 31. And then there's 4 oxygen, so it's just 16 times 4. And this will give you an overall of about 149. Okay, sometimes you will get formulas of like hydrated salts. For example, they have a H2O at the back, so like magnesium sulfate, the hydrated magnesium sulfate, so it's MgSO4 7H2O, right? To find the molecular formula of such compounds, it is the same way, right? You just tabulate all the atoms and then you just multiply it by their relative atomic masses. So for this one over here, just rewrite the formula, right? You can actually find the formula, the molecular mass, by taking 1 times 24, right, plus, because there's only one magnesium and then there's one sulfur, so it's just the 2, plus 4 oxygen, so it's just 4 times 16, right, and then plus 7 H2O, so there's 7 overall times, okay, there's 2 H's and 1 oxygens, right, in the water molecule, so it's 1 times 2 plus 16 over here. So we add this all up together, you get a relative molecular mass of about 246, which is pretty high, right? So don't be surprised if you ever see solids or that are hydrated and then you have this additional H2O, right? We just calculate it normally. Okay, so next we want to calculate the value of X in CuSO4.XH2O, where like the number of water molecules in a hydrated salt are like an unknown. So given the MR is this, right? Now we're just going to do it the opposite way. So we know the MR of like CuSO4XH2O, this is equal to, so you do it normally, right? So we know copper is like 64, right, plus 32 plus 4 oxygen, so 16 times 4, right? But now it's plus X times H2O, which is 1 times 2 plus 16. And we know this overall value actually equals to this 250, right? And then it's just a matter of doing basic math and algebra to solve for X, right? So we know that actually 250 minus 160 after this is equals to X times 18. So we can tell that X is actually 90 over 18, which equals to 5. And this is how you solve for X over here. If you enjoyed today's video, do remember to click the subscribe button so that you can enjoy more free content from us and improve your chemistry with us together. If you want to join my community of students to learn more secret formulas to acing chemistry, do check us out in the link below and sign up for a free trial class today.